What I want to talk about is a little bit what Planit is, why we're even around, what the motivation is about Planit existence, the goal that we pursue on projects with the project teams that we're working with, the process, what we do, and then the results of what comes out of it. The reason why I'm here is the goal of Planit and why Planit even exists is exactly that, to improve productivity on the job site. It's like this better? Okay. So my background is I'm a structural engineer from Germany. That's also where I got my accent from. And 20 years ago, I moved to the Bay Area in San Francisco after having worked only a few years in design in Europe, and then joined Webco Builders there as one of the largest general contractors in California, and then worked for them for 10 years, then 10 years as a vice president of operations for Suffolk Construction in the same area. 3 years of that, I actually worked as a concrete contractor for Webco Concrete, and we built the Cathedral of Christ the Light. I only had half an hour, but because he gave me an extra little bit of time probably because people will show up, I want to share an anecdote of how actually I came to found Planit as a source for a problem that we found on most projects. We were building the Cathedral of Christ the Light, and I was was the project manager for the project. It's a beautiful cathedral designed by SOM at the Lake Merritt in Oakland. It's architectural concrete. It's a cone-shaped cathedral that has two big reliquary walls that go around the entire project, and then the windows are actually cone penetrations that actually penetrate through the other cones. So they're three-dimensional integrals to actually create the window openings. When we tried to detail that in a ramp, a garage ramp that actually went around the cathedral on the inside in the mausoleum to actually go up into the parking areas, the information was simply not in the drawings. We tried to detail it, and there was a moment when we had the wall forms standing up, the window box had to be built, and we couldn't figure it out. We had written hundreds of RFIs, and the design team insisted that it was in the drawings. There was a moment in time when the walls were standing there for literally 6 weeks, and we couldn't figure out the wall openings. It sounds absurd, but that is what happened. And I actually sat with the design team, and I said, I won't name names. It was not SOM, it was a construction administration team. They said it's there. I sat with them next to them on a drawing table, and I said, well, we're just dumb contractors. I do not know how to actually put these numbers in. Please do it. And they were explaining, well, you just take the numbers from here, it's on this sheet, and then you flip to that sheet, you look at the architecture, it's here, the structure here, and it's there. I said, no, sorry, here's a pen, please do it. 2 hours later, they left the room, they said, it's really not in there. The claim was $3.5 million just in GCs and delays. 8 months of delay on the project from the drawing set for just the information wasn't in there. 223 days of delay is what we had in the delay claim. 8 months it took us to actually work through this. So the productivity impacts that we actually have on job site, I learned the hard way, isn't necessarily just the link beams and the rebar design. There's nice stories around that as well. But it is, how do we actually communicate the constructible design? How do we make sure that it is complete and that it is actually consistent and that the drawings are actually buildable? And that's why I founded Planit. I realized over the course of the experience that I had that this almost every project suffers from the same problem, that when we actually get into the field, we need thousands of RFIs, and that's not exaggerating it, to actually build the project. And so how do we actually make that better? So the goal that I had was have a buildable set in the hands of every craft out in the field to build without having a question. That's the goal. Today, Planit has roughly 300 employees. We've completed over 200 projects, and we work for general contractors. That's where we started. From there, we were lucky enough that developers hired us to actually produce the results that we have with a buildable set. And then rewarding events happened where actually trade contractors reached out to us and said, hey, we love these drawings. Can you make one for us when we go into the next project? And then in the last few years, we've actually had architects that also hire us for actually having that same experience. The question that the architects actually came to us with is, why are your drawings buildable and ours are not? Why does it take 1,000 RFIs to actually go out in the field and build? And why can Planit produce a drawing set where you have few questions left? I do not want to say zero. We make mistakes. We're still humans. But what is it? What is the difference there? And that's what I want to talk about today. So what's the goal? The goal is Jeff Gouveia, he was at the time, I think this was in 2017, the general manager at Suffolk Construction, actually here in Boston, in the headquarters. And he said the core of all evil, because I present a lot to design teams, just like today here, I added and opportunities lies in the contract documents. If the contract documents didn't have any issues and we could take them, read them, and build what's on those documents and go into the field, we wouldn't have any, we would do a lot better. I'm not saying we would close the gap and have the 400% increase in productivity, but we would have a significant impact on it. I'm thinking maybe 5, maybe 10% of increased efficiencies if we could actually deliver a drawing set without any issues. And as I promised, we will talk about the results, and we have actually some studies that we did with our clients. This is a graph that Carrie already showed, and I have this always in my standard presentations when we implement the process. I'm not using it to explain the problem that we have in the industry. This is the productivity of the construction industry compared to the non-farm industries. So we're flatlining. Everybody else has increased. The gap that you see here, this gap is 300%. So I'm always using this as an excuse to say, if we do things differently, sorry, if we keep doing it the same way, we end on the bull's horns. We didn't want that. So it's my excuse to say, okay, what do we need to do differently? This is I'm now switching to why and what's the motivation behind it and what is the approach to actually address constructability from a very geometric concept. And what are the processes that we need to change to get there? So first, what are we even trying to do? This is a diagram that Patrick McClamey with HOK developed, I think in the early 2000, 2005, somewhere in that range. And he said, okay, the ability to influence design decreases over time. This is the life cycle of a project from programmatic design phase to design to a construction documentation operation. And the cost to influence this goes up. Basically, if I want to add air conditioning to a project and I'm in conceptual design, it takes 2 pennies because I need to write down HVAC, and I then put that on a napkin, and now I've added it. 2 cents, we're done. If I do that, and we've done this, as a late decision after I've built the podium, and now I'm doing a type 5 structure on top of it, and talking about actual things that happen, and the owner decides they want air conditioning in the building, that's expensive, and you have very limited ability to actually even do this. Yet, most of the effort in design happens in this phase. That's what at the time they said. And so it's at the time when cost is already pretty high and the ability to influence them is pretty low. So how about we move it to the left? That was the idea in 2005. At that time, many design teams started to use building information modeling. Designers started to work in Revit. That's what happened. 10 years later, we accomplished this. I think we actually moved to the right. We didn't move to the left. If Bruce had given the presentation before, I think he would have strongly, violently agreed. The drawings are not becoming better, and since we review our drawings and we make them, we correct them, I can state that drawings overall in the industry haven't become better, they've become worse. And I'm sorry that I say this in this audience, but there's good news. So what happened? When we when we talked with design teams, we learned 25% construction administration in the past, 75% of their efforts are spent in design. Today, 40%, and I made this slide also in 2017, 60% in actually design. So the effort is moving to the right. When I present this today, maybe in the room, if we have designers here, now people say it's 50-50. So it's actually moving further to the right as we go. And when you look at the actual hours we spend versus the cost, the actual budget of hours that actually go into the design is actually decreasing. Budgets for design are shrunk more and more, and delegated design is becoming more favorable, and design is pushed always to the tail end. Like, you can always object, and I'm happy to learn more, but that's what we learned from designers and owners. So we as I said, we work for a large general contractor. Our clients are Skanska, Webcorp, Suffolk Construction, Greystar, like related, like many of the very large firms. And so we're lucky enough that we have access to a lot of data. And what I'm showing you here is like, so what does this do with moving the curve from the right to the left? How do we actually accomplish this? That's what we set out to do. Here is a project that we were not involved in. This is Procore data that we download from the big servers. And what we're showing here is all the questions that I asked on the project until we close it out. What you see here is in orange are the RFIs asked in Procore by trades. In green are the RFIs asked by the general contractor. What do we see? We see a big ramp up. Oh, and then the red box here is construction start on level 1 on a 20-story high-rise residential building. So what happens? The subcontractors ask the questions, and then the general contractor asks them, and you see the timely delay here. What is that? It's the subcontractors ask the questions when they're detailing and they're procuring materials, so they're a little bit ahead of the game, so they're asking those questions. When they show up in the field and actually install it, that's when they realize it doesn't fit. That's when the GC starts to ask the questions. That's why you have those questions. So what do those have in common? They all happen in construction. When you see this here, we basically list them over time. And you can see that 80% here of all the questions are actually in construction. Here are the numbers. A good dozen of questions before construction, over 100 questions in construction. What we do is, when we implement planning control, and we assist those projects, then you see in the same time frame, it's a different project, level 1, also residential project, I think this will have 15 floors. You see a steep ramp up of resolving issues in the document set. Then, because design is typically still evolving a little bit, it flattens off a little bit. And then here, we monitor, same Procore download, the questions from the trades. So there's still a few trade questions, but now we have a dozen of questions in design, in construction, during construction, and everything as before construction. So when you compare those two slides, this is how we move the curve to the left in a very drastic way. So what is it and how do we do this? I want you to do the same thing that you tried, Karen. So what I want to show you now is like, what is it actually that we do? How do we get to this drawing set when we say that, hey, we have one option? What I showed you is the result of having design documents that constantly evolve. Bulletins, ASIs, tons of RFIs that get issued. In the meantime, there's an army of people that actually creates fabrication drawings. And those fabrication drawings, oftentimes as designers, we don't even see. I might not have mentioned I'm also a licensed structural engineer with a professional license in California. So I know a little bit about the design side. So the drawings that we actually use in order to fabricate things and the drawings that get produced, thousands of drawings that happen while we're creating these ASIs and bulletins and RFIs. The design teams believe that, well, we can actually finish the design, and as long as we have a design drawing right there when we actually go bid, good enough, but we have the fabrication detailing process that happens in parallel. And that clash and that friction that area you talked about is what is the inefficiency in the industry. If I continuously try to update these fabrication drawings, then of course I'll end up with issues in the field, because there's no way that you can update those when, like, some design team, some project teams decide that the best way to catch up is to have a regular bulletin be issued once a month or so to actually catch up with all these RFIs that were being asked. But that's a new drawing set. So what I'm showing you now is an example of one drawing. This is actually in Washington, D.C. Just the issues that we actually resolve when we show those. It's just a few of thousands of issues that we resolved on the project, but it gives you an idea of what actually is in the drawing set. You see this model, right? That's the design that we have. It looks very complete, very detailed. When we look under the hood and we actually dive into the detail, we see the problems that happen in construction. The first thing that we're looking at is clearances, including ACI tolerances, and egress and exit requirements in this design. You see a conflict between the egress zones and this concrete column that's Planit. In order to resolve this, we changed the furring type. We still have a little bit of an issue left. There's another inch, and now we move the window wall in. This is a conflict of construction tolerance that we include and egress and exit requirements. Here's an example for a typical unit. A structural steel support detail that wasn't quite coordinated with the architectural layout. So quick change, now we can actually use it. Then these are all things that are in the design document, 100% CDs, right? So I'm not making those up. So here's a typical unit, a concrete shear wall. Here again, 117 tolerances. Issues with acoustical requirements for a chase wall. Now we need to make the chase wall a little bit wider. It moves the kitchen cabinet. When I move that, it moves the adjacent bathroom wall. Now it causes issues with ADA clearances in the bathroom. In order to fix that, I need to change the kitchen cabinet. Had I built the concrete shear wall and the partitions before I put the kitchens in, I don't have a way to actually solve this anymore. Now I'm modifying 300 kitchens in this building. Here's a good example for just continuation between floors and having chase walls and basically completeness and finalization of design. So that's how it really needs to look. Then the next one is the concrete columns that are conflict at a stair. So here's a stair railing that needs to be detailed. There's a concrete column. You ask an RFI and you get an answer back. Just move the column. Now it works. Not so much on the floor below because you just moved it on the landing. That takes a little bit longer. And you need to now imagine typically there would be project teams sitting there and they need answers and this is what they're getting. So we do this all ahead of construction, right? So this is now half a year before we even go there. And so here's a good example for a storefront. It looks very complete when you look at the design documents. There are curbs, there's built-up slabs, ramps, everything is shown. But when you look under the hood, what do you really have? And you see all these conflicts. Beams not aligned with openings, openings and ramps not aligned. We have concrete curbs that need to be, here's a beam that needs to support a ramp but didn't quite make it to the ramp, so that needed to be elevated a little bit. The beam was also not needed down there, so we lifted it up. Now it actually works. Structurally, the same thing. Then we have a built-up slab and a ramp that weren't aligned. And then the next thing is that we need to have an opening right in that same location that supports the CMU wall up above, so we need to make the curb a little bit wider. Once we're through all of that, then we have a curb that's fully coordinated that can actually receive the storefront, and now we have buildable design. But quite an effort to go through, and if you do that during construction, the inefficiencies are very, very intense. Here's openings that we're just missing in a concrete shear wall. Again, like it sounds, partially when you look at this, you kind of scratch your head like, how can this even be? But this is just the projects that we have. We have 200 of them. They all look the same, more or less. Here's a good example of construction tolerances for exteriors. It happens on almost every project. So when we actually apply the construction tolerances at the edge of slab, we often see conflict with vertical elements and the actual enclosure. Then creates issues with fire safing at the edge of slab, oftentimes just accessibility and constructability in the field. Once we resolve those, there's 150 of those locations throughout the entire project. Sometimes we miss one, and then we're surprised how expensive that is, and the amount of fixes tells us like what actually the amount of cost is that we have. There's so many changes that at the end of making all of those updates, we actually extract a new drawing sheet. We issue that as an RFI, and we say to the design team, please confirm. Then we do MEPS coordination. That eliminates the issue that many design MEP contractors tell us is that, hey, all this BIM coordination doesn't help us if the framer doesn't frame what's on the drawings. The reason that the framer doesn't frame what's on the drawings is what you just saw. In the field, they need to make the corrections at some point in time, and then you wonder that the next subsequent step doesn't work anymore. So what you see here is, I think I showed this on an earlier slide, when we issue the revised drawings as an RFI, we color code the dimensions. Red dimensions are the dimensions that were missing from the design document set. Blue dimensions are the dimensions that we actually had to change due to conflicting information in the document set between disciplines, between sections and details and plan views, and large plan views and regular plan views. Then black is what we didn't have to change. We typically change between 60 and 90% of dimensions in a document set in order to make it work. Here's the curious thing. When you think about this, you have typically sometimes between 500 and 3,000. We have a hospital where we have now 5,000 RFIs. I have to say that one very sad revenue stream that we have is that we are asked to analyze projects that went sideways and are in claims. Then we are asked to actually analyze this and do a post-mortem analysis, and that's why we get a lot of the information from as well. We change between 60 and 90% of dimensions that are in a drawing set that are somehow conflicting and need to be corrected to have a consistent outcome. So what is the result? Anecdote is that Suffolk Construction started to implement the process in 2013 on the West Coast, monitored it for 4 years, decided to roll it out to the entire company, and then at some point in time they were tracking at 60% implementation, and they said, let's actually, before we decide to push to 90 or 100, let's do an analysis. They wanted to know, is it actually making an impact? And so they studied 53 projects, and this is the graph that they came up with. And, what it basically shows is that they compared 53 large commercial projects over 100 million and monitored the PCO count, so potential cost impact or change impact in cohort, the RFI count, and the TCO delays. They saw on average 53% decline in PCOs, 54% decline in RFIs. I have to say, we don't take the RFIs away, we just put them before construction. So if you look at the actual elimination of RFIs during construction, we track more like in the 90% range. And then TCO delay was reduced by almost 80%. There was a more detailed breakdown of this. The TCO delay had multiple categories. There's the unforeseen conditions, and then there's one group that was design delays, meaning that there's impact from design deficiencies that basically go back to the owner team, and they were completely absent on Planit control projects. So what do we actually do? What is the difference? And this goes into the completeness and the change in how we work. what I show here is basically the detail on like how the process works. I'm not sure if you can read this. There's the design documents. It's a standard process, and we do submittals by submitting product data and then the fabrication drawings. Then we have a lot of BIM modeling typically on projects, and why we do this, we ask RFIs. I show this as this confetti because RFIs are being asked typically when one trade wants to actually create a drawing. So the concrete RFIs come first, then 6 months later we see the kitchen cabinet drawings, but they kind of have an impact to each other, as we know. Then we make all these fabrication drawings, and then we go into the field and ask more RFIs. Question is, if we did all the BIM modeling, if we did all these fabrication drawings and planning, why are we still asking RFIs when we're actually in the field? When we do planning control, we have a different approach. We start with the same concept of product detail, but then we organize the entire communication topic that was said, like how do we actually change the behavior and the information flow of all stakeholders on the project between owners, architects, engineers, and fabricators. So what we do here is we call it the input checklist. We actually collect all fabrication details. We include construction tolerances and any type of code requirements that typically needs to get checked at the end one more time, which is ADA, egress and exit, and all those things. So we do this in a very organized way. And then we create one centralized file that is actually the fully coordinated file. And then with parametric detailing, we actually extract all the fabrication drawings. That is why we don't need the RFIs in the field afterwards, or very, very few of them. So what we're eliminating and what we're changing is we don't ask every trade to create their fabrication drawings after the design is given to them, but we actually just ask them for the expertise that they bring, their fabrication details, their knowledge of how they actually want to build it, the construction tolerances that we need to include. That is how we actually combine them. In order to implement the technology, we've written an application for that so that we can actually manage that communication workflow. And at the end, the outcome of that is that we are actually able to create a single source of truth document set that doesn't have all the issues in the field afterwards. To summarize it, oh, there's one more thing. Do I have another 3 or 4 minutes? To summarize it, there's a conventional process where we have design documents. We call them maybe 80% complete. If designers are in the room, we call them 90% complete. The point is they're not 100% done. And then we have dozens of trades that actually start the fabrication detailing process. The problem with that concept is that they all fill in the gaps some different way. They all give their best and they all have very good knowledge. But how do we build one building if we have dozens of trades filling in the same gap in a different way? And then these drawings typically go to a completely overwhelmed construction administration staff that has maybe 2 designers still left on the project and then like a couple of PMs that need to review this. But let's be honest, if we have a stair opening in a high-rise building, I get concrete shop drawings, I get a metal stair drawing, I get a standpipe drawing somewhere. All of those are dimensioned off of different grid lines, they're different, off of different information. I have 2 ASIs that I received that also impacted those, and probably by the time that the stair guy comes around, 300 RFIs. And then there's a PM that needs to check whether they have the right information. So what they do is they put a stamp on there and they say, you need to follow the contract documents, but oh wait, they were only 80% complete. The process doesn't make sense. That's where the bull and the horns and stuff comes in, is that if we don't change that, we will never come to a better place. So what we've changed here is, and then by the way, when you go on site and you want to quality control what actually has been laid out as a superintendent on a general contractor, you have the option of looking at 12 different drawings that all show you different information. You cannot quality control if the opening is actually right. You can quality control it again, one of those drawings, whether it's the right information is left to be seen. So the CL process in planning control changes that approach. We have a design document. You saw that. We make one drawing. The designers approve it as an RFI, and all the trades actually sign off on the same drawing. So we turn the table. Instead of having many drawings reviewed by a few, we have one drawing that gets reviewed by many. That's how we achieve that. It's not Planit having a miracle detailing team. It is that we've changed the process from creating a single source of truth that is reviewed by many, rather than having multiple sources of truth that nobody wants to sign off on, and that try to build one project. What's the outcome of that? We can actually use now layout technology today that actually prints this entire drawing thing in like 4 hours on a plywood deck. We've done this on a project that we worked actually with Kerry on 1900 Broadway. Doesn't work. Anyways, what I want to say to that, maybe it doesn't. What I want to say with that is that we now have a drawing that I can use for quality control. Better yet, why not just print it without any additional input and room for error, with a robotic layout in the field and use it for that. So now we have efficiencies that we can create in the construction process because we have a single source of truth that we all agree to and that we have aligned on that we want to actually build. Okay.